Hello everybody. I'm sorry for ending the previous video abruptly. It's just that my battery died. So I just got shut off like that. So we'll continue. I was talking about the length of a curve C between, so this is a parametrically given curve, between two values of the parameter t and t1, right? So if you have a curve in R3, there's a little picture here, x, y, z, and you have some curve, and say this is the value, this is a point x of t1, y of t1, z of t1, and that point is x of t2, y of t2, z of t2, right? So this is a curve C is given by x of t, y of t, z of t. So you might ask, what is the length of that piece of the curve? And then from our considerations here, you saw what we did was we divide this curve up into really small pieces so that each piece looks roughly like a part of a straight line, and then the length of such a piece is that, essentially, which follows from the Pythagorean theorem, which you can then convert to this using just simple algebra, and as delta t goes to 0, these turn into derivatives. And normally you would add up these lengths of these pieces, but in the limit, the sum turns into an integral. So one gets the length of C between t1 and t2 given by equal to the integral from t1 to t2. What do we get? Well, we get the square root here, and all these guys become derivatives. So it's x prime of t squared plus y prime of t squared plus z prime of t squared dt. So let's compute it in a few examples, the ones that we actually talked about in the previous video, in the previous part of this video. We had some very simple curves. The first one was a line C of t given by t. So this is a line, right? And as we said, this is the line that goes sort of at equal, in equal way in the x, y, and z direction. So suppose I want to know what is the length of the line. Of C between t equals 0 and t equal 1. So essentially this is going to be just the length between. So when t is 0, I get this is just the origin, and when t is 1, I get this. So you know, because this is just part of a line, we could just use this formula for the length of a line segment in R3, and we would just get that this length, so I guess the distance in this case, d between C of 0, C of 1, is equal to the square root of 1 squared plus 1 squared plus 1 squared, which is the square root of 3. Okay, but we could also apply this formula. To apply this formula, so alternatively, apply star, let's call this formula star. And so what do we get? Well, remember this is x of t, this is y of t, and this is z of t. So we compute all the derivatives. So x of t is t. So x prime of t is 1. Y of t is t. So y prime of t is also 1. And same thing with z. So this length equals the integral. Well, so the t1 is 0, so it's integral from 0. t1 is 1 to 1 of the square root of the squares of all these derivatives. So 1 squared plus 1 squared plus 1 squared dt. Well, that's just square root of 3. So that's square root of 3 as a constant I can take out of the integral. And this integral is just equal to 1. So, of course, I have to get the same answer. So I'll leave this formula up here, and let's consider another example. The one when we had so this is the length of C between t equal t1 and t equal t2. So in the second example, we had, so I think it was actually the third example when I did x was t, y was t, and z was t squared. So remember, the graph of it looked like this. When I project the graph of this curve onto the xy plane, I just get the line y equals x. However, as you, well, I think I maybe marked this in orange. However, as you keep moving, if you keep changing, going from with t from 0 up, you see that the z-coordinate goes up, and in fact in a quadratic way, so you get a parabola that looks like this. So again, I want to compute the length. So the length of C between t equals 0 and t equals 1. So essentially this bit here, right, when t is 1, the coordinate of the point at x I get 1 and y I also get 1. So going up to the parabola or somewhere here. So I want to know how long is this little arc here of this parabola. So this is now not a straight line, so I cannot just simply use the formula for the distance between these 2 points. I actually have to do this. All right, but let's do it. So here in my formula, x of t is t, y of t is t, and z of t is t squared. Right? X, y, z. So the derivatives are 1, 1, and 2t. So this length will be equal to the integral from 0 to 1 of the square root of 1 squared plus 1 squared plus 2t squared dt. So that's the integral from 0 to 1. 2 plus 4t squared dt. I'm not going to compute this integral. If you want to, you can try to do it. It's a doable integral. Not too easy, but doable. You can use a certain substitution to get this done. But this already shows you that even though this is quite a simple curve, like this parabola, the formula for the length is actually, comes out, it gives you an integral that is not a trivial integral. And this is in general the case. You see, the formulas for length of curves, even quite simple curves, are quite complicated. That's because you're doing sort of two things. You're first doing the derivatives, you're squaring them, and you're taking the square root, and the square roots of various expressions are usually very difficult to integrate. In most cases that you would encounter, they're actually impossible to express explicitly. So very often one just writes down that formula, and if you need to compute the length of a curve in practice, you just use some sort of approximate method of integration. Okay, let's do the last example, the spiral. So in this case, C of t was given by cosine 2 pi t sine 2 pi t t. And again, I want to know the length of t, length of c, between t equals 0 and t equals 1. So that means on the picture, I'm starting out at 0, 0, 0, and I'm doing one rotation to 1, 1, 1. And I would like to know how long this arc is. Note that the circle has radius 1, right? So if I project it down onto the xy plane, I just get a circle of radius 1. So the length of that circle, when you do just one revolution, must be equal to the circumference, so it would be 2 pi. However, because this is a circle sort of stretched also in the vertical direction, you can expect the length to be larger than 2 pi. All right, well, let's do what we have to do. So x of t is cosine 2 pi t, y of t is sine 2 pi t, and z of t is t. So let's do the derivatives. So x prime of t is going to be minus 2 pi sine 2 pi t. Y prime of t is going to be 2 pi cosine 2 pi t. And z prime of t is going to be 1. So this length over here is going to be the integral. You don't have to, by the way, go between 0 and 1, right? You can go between any 2 points, but just, I don't want to do too many examples. Let's just stick to 0, 1. So it's the integral from 0 to 1, the square root of, I have to square all of these derivatives. So that's going to be 4 pi squared sine squared 2 pi t plus 4 pi squared cosine squared 2 pi t plus 1 squared dt. So that's the integral from 0 to 1, square root of, let's see what we get here. If I take out 4 pi squared from these two expressions, I get sine squared plus cosine squared. And sine squared plus cosine squared is 1. So these two expressions simply give me 4 pi squared. So that's 4 pi squared plus 1 dt. And we're lucky here because this is a constant. So I can take this out. And I get 4 pi squared plus 1, the integral from 0 to 1 dt. And that integral is 1. So the length of that one revolution of the spiral is 4 pi squared plus 1. Note, had this 1 been 0, you would get the square root of 4 pi squared, so that would be 2 pi. And that is exactly the length of the shadow of this one revolution of the spiral when you project it down onto the xy plane. This plus 1 takes into account the fact that you actually go up vertically here. All right, if you wish, you can do other examples for yourself to just get some practice with this, or look at some old exercises from multivariable calculus. That will be quite useful for us to know how to compute length of curves.